Right, gang, I'm back. Long time no see. Today, we're hitting you with the mifepristone synthesis. You already know what it is. We already know. If you're part of a big company, don't sue me. You're not going to get anything. I have nothing. But here we go. Let's get started. Today's synthesis explores some really very interesting chemistry. We're starting off with this already somewhat worked on hormone. As we can see, there's a protecting group right here. We know where that came from, and we'll have to deal with that a little bit later. On our first step, though, is selective epoxidation of one of these double bonds. The double bond near the protecting group will be selectively epoxide by our peroxide, and I think that the solvent here will have a directing effect to that alkene, because both of them seem very, very chemically similar. The only thing I can think of is the one that will be epoxidized is closer to, that sort of ketal type functionality, which will potentially have some sort of effect on its chemical environment, leading to that selective epoxidation we see there. And that's some great chemistry there. Really, really fantastic. So now what we're going to do is hit it with a classic Grignard of the acetylide ion. And we know all about making Grignards here. It's the wrong, forgot one carbon there. But the acetylide is going to go ahead and attack that, ketone. It's going to be I believe, hard nucleophile, electrophile type interaction. So it'll form a good bond. We're going to hit it with a aqueous workup to get us our alcohol type functionality. And there we go, we're moving one step closer. The thing about this reaction is that this bond is going to be racemic. This will form a racemic mixture. Some of the bond is going to go forward, some will go backward. Separating it from there, basically impossible. I didn't research further, but that does lead to the question of whether, when this is available commercially, if it's offered as a racemic mixture, I doubt that in industry they go through the effort of, separating those two. That would be very, very difficult to actually do. Let me not forget to change up this epoxide here. Now here we have another Grignard coming in, and this one is going to be really fun. So what we're going to do here is bring this aniline derivative in with a Grignard. We're not going to go over the chemistry of how to make those here. There is some interesting chemistry to be had, but most of it is just forming complexes in an ethereal solution. It's all great chemistry, but today's focus is where and why some of these reactions are occurring. And here we know that the carbon on the Grignard is going to be nucleophilic, and we see a great place for it to attack, but the question is why, because this is kind of a bulky substituent. It does have room to come there, but if you notice that this alkene is relatively near a epoxide, and that has strain, especially an epoxide within a ring system that's really strained on some of those epoxide carbons. So this alkene is relatively uh, nucleophilic towards the epoxide, because if it reacts and comes over here and opens up the epoxide, that strain is relieved. And that's the motivation for the nucleophilicity of that alkene that we see there. So the grignard is going to be even more attracted to that double bond. That double bond is going to come towards the epoxide and open it up. From there, we're going to have, it's a lot easier to just copy and paste. So let me go back and fix up some of these bonds. So we got the squiggly there to our acetylide. We got this double bond moved over here. This opened up to, or the opening of the epoxide there. And we have our sort of, no, that's not the best. Our aniline derivative here, and that is an awful benzene. We'll go ahead and try that again. And it's so much bigger than the other ones. Okay. We'll just leave that there. Perfect. Almost done with this. So here is another great step. Deprotecting. Here we're going to get a twofer on this one. Hit it with some acid. And we're going to not only deprotect that, but we're going to protonate this OH to kick it off and form an alpha beta unsaturated carbonyl system. How great is that? Fantastic. So let's go back and fix all of our little changes. OH, acetylide. Here, this is there. That is actually gone. So is our protecting group. So now here, and look at that. Alpha beta unsaturated carbonyl. What a great reaction. What a great formation. Very amazing. So here is, oh wait, we forgot our little aniline derivative here. So let's go ahead and add that. Perfect. And now, as we said earlier, we have this racemic portion of the molecule. The one that we want is the one facing backwards, but to actually separate that, we're going to have to sound off on the chat on how to do that, because that's going to take a great deal of effort. And if you ask me, off the top of my head, I don't even know what would work. So go ahead and sound off if you have any ideas. And as per usual, don't try this at home. Don't do this. It's never worth it. We're just here to talk about theory. We're here to talk about how these things are made and what's the motivation for making them. We know with this alpha beta unsaturated carbonyl, the motivation is the larger area that the electrons have to move around in, because they're delocalized. They got all this area. You see those pi electrons can move all over there, and they love it. And that's what drives that reaction forward. So great. A lot of great chemistry on display here. Please be safe. Please, happy holidays. Have a great time. Have some time off. And thanks, y'all. Hopefully we'll see each other soon.